record. Okay, so everybody, welcome back to the String Fien online seminar series. Today we're very happy to have for the first talk Fien Apers, who will tell us about backtracking AdS flux vacua. And please take it away.
Okay, thank you for having me. So yeah, I'm going to talk about backtracking AdS flux vacua. This is based on this paper I put online in June together with Miguel Montero and Irene Valenzuela. And I also talk a little bit about a follow-up more recently. So just to explain the title, so backtracking AdS vacua or flux backtracking is the algorithm with which we start with some AdS flux vacuum. And then as an output, we get a singularity in a brane picture that once that on these D-branes, the holographic dual of these AdS vacua will live. So the plan of the talk is as follows. I will start by introducing scale separation in the context of the AdS CFT correspondence. Then after which I will explain you the flux backtracking algorithm, and I'll apply it to some simple examples where we know what we should get to then apply it to the scale separated AdS vacua. Then lastly, I'll preview a bit on like how to complete this flux backtracking for the DGKT vacua concretely, and how you can use it to test its decoupling. I'll be very brief on the last part because this will be discussed next week in the Harvard online seminar in more detail. Okay, so in the AdS CFT correspondence, how do we usually or like historically derive AdS CFT pairs? Is we start from a brane picture. So we start from like a stack of D-branes, which are like either in flat space or probing some singularity. And then by looking at these D-branes from different perspectives, we can derive the AdS CFT correspondence. For example, we can look at the near horizon limit of this geometry where we find AdS vacua, or at the world volume theory of these D-branes, where potentially a conformal field theory lives. And then these two perspectives must be equivalent, and that's how we get to like AdS CFT holographic pairs. Now, in string phenomenology, like when we do string compactifications, this brane picture is usually not what we have at hand for AdS vacua. Instead, we have like a low dimensional effective potential with an AdS minimum. The main AdS vacua of interest for string phenomenology are scale-separated AdS vacua. So these are AdS vacua where the length scale of the internal dimensions, the Kaluza-Klein length scale, is much smaller than the Hubble scale of AdS. And this is an important requirement to get an actually lower dimensional effective field theory. And this is maybe like one of the most basic requirements we can put on a string compactification for a string phenomenology. It's maybe like more simple than getting like, for example, the standard model. So it's worth just like focusing just on this scale separation property. Obtaining scale-separated AdS vacua from compactification is not straightforward, and we only have a handful of constrictions, like the KKLT, LVS, and DGKT vacua, and even for them, there's no full consensus yet on their consistency. And the scale-separated AdS vacua are also very interesting from the AdS CFT perspective, because well understood AdS CFT pairs like AdS 5 cross S5 in type 2b and the duals or other front Rubin vacua or like ABGM, they all have like internal manifolds that have like approximately the same size as scales as the AdS vacua. So they are not scale separated at all. And so we can ask the question, does AdS CFT actually require these large extra dimensions in string theory? Do we need like AdS times some large manifold to be dual to a CFT, or is this not needed maybe? And do we have to like actually find an entirely new class of conformal field theories? Because these scale separated CFTs, they also have like quite peculiar properties. And like the main characterizing property for a scale separated conformal field theory is that there must be like a large gap in the spectrum of single trace operators. So I have like a schematic figure of like such a scale separated spectrum here. So the operator dimensions are going from left to right. So we can have like a vacuum state, maybe like a small number of light operators, which are like dual to the stabilized moduli. But these must be separated by a large gap from all kinds of heavy stuff like the Klein modes. And there are no known conformal field theories with this property. Okay. So as like a step forward to try and find these holographic duals for scale-separated AdS vacua, we introduced the flux backtracking mechanism. So this flux backtracking should be like more generally valid for also non-scale separated AdS vacua, but the scale-separated AdS vacua and the motivation. So with flux backtracking, we start from these AdS vacua, then try to find back the brane picture. More concretely, it will give like the singularity that needs to be probed by D-branes. And then hopefully in the future, in a further step, we can learn something from the conformal field theory starting from this brane picture. Okay, so I'll now show you the algorithm. It's quite simple. It just consists of 4 steps. Okay, so this first step is, as I said, we start from this effective potential, which has like internal moduli, which has like an AdS minimum. Of course, to actually have like a real lower dimensional effective potential, it's important to have scale separation. But often there's also like some kind of consistent truncation, so that talking about a lower dimensional potential makes sense. And then we're gonna have a closer look at this potential and look at which things are contributing to the potential. And we'll try to separate these into 2 classes. So first we have like a flux, a large N flux. So again, this is a flux that can be scaled up so that we can turn this flux into like D-branes. So this flux we turn into D-branes. And then these D-branes need to probe a certain geometry, which we imagine is sourced by the residual ingredients. These residual ingredients could be like some curvature contribution, other fluxes, or like some orientifold planes. And these residual ingredients are the ones that lead in like the asymptotic tail of the potential. And then it's like where like you have like this interplay between the large N flux and these residual ingredients where you get like the AdS minimum. And so the trick we suggest to find this geometry is to simply remove the large N flux from the scalar potential and look at the potential sourced only by these residual ingredients. So then we remove then actually like the AdS minimum and we get some runaway. And then the job is to try and find like this runaway, like it is like actually some kind of dynamical cobordism, and we want to find the geometry this represents. So to find this geometry, we'll assume there's like some kind of supersymmetry or at least fake supersymmetry. So we can write down a superpotential, and then we solve for the domain wall flow, like the PPS flow equations with this superpotential to get a D-dimensional metric with a running scalar. And then in the very last step, we uplift this D-dimensional metric to 10 or 11 dimensions. So we'll assume that there's like some uplift ansatz that is like quite simple and depends on like the moduli in this way. To make it more concrete, I'll discuss like an almost trivial example. Like these are like the AdS5 because it's 5 vacua in type 2b supergravity with n units of 5-form flux. And there it's very clear how to make the split into the ingredients. If I write down the scalar potential in terms of the breeding mode or like the overall volume, there's 2 contributions. There's the 5-form flux and the curvature. The 5-form flux is the one dual to the D3-branes, so this one we want to take out and turn into D3-branes. And then we want to look at the geometry sourced by like the curvature left over. So we can simply solve for this flow. We find like some profile for the moduli. We get like this 5-dimensional domain wall geometry, which then uplifted to 10 dimensions takes this form. So like I've written it here in terms of like a rescaled radial coordinate, which is the orthogonal distance to the D-branes. There's the flat part, a non-compact part, which is along the D-branes, and then we have the extra dimensions. Of course, what we obtain here is just like 10-dimensional flat space, as we should find. For like slightly more general compactification, where we don't have like a spherical internal manifold, but maybe some orbifold thereof, you find like a conical singularity, which is exactly the singularity which needs to be probed by D3-branes to find the dual. Okay, so this example is very simple. And in the paper, we checked some more examples, some other Fern-Rubin vacua, for example, or ABGM vacua, or like 6-dimensional AdS vacua, also in massive type 2A. Okay, and now I want to apply it to scale-separated AdS vacua. I'll be focusing on the DGKT vacua. So the DGKT vacua are like AdS4 vacua we get from compactifying massive type 2A string theory on a Calabi-Yau manifold. And there's some simple ingredients. We have 3 types of fluxes. So 4-form flux, there's the Romance mass, and some 3-form flux. And there's also orientifolds or 6 planes, which like provide the necessary negative energy density to evade some no-go theorems. And these O6 planes, they induce a tadpole for some of the fluxes. So for the Romance mass and the H3 form flux. So they're involved in this tadpole condition, meaning that implying that they can only like take like a finite number of discrete values. But the nice thing is that the 4-form flux is not bounded. So we can take them to be proportional to some large n parameter, which we can dial up at will. And then so these fluxes and the orientifolds, they generate like a scalar potential for the moduli. I've just written it here in terms of the universal moduli. So there's the volume modulus and the dilaton. And these fluxes stabilize the moduli at parametric control. So it means that once we scale n to infinity, then we'll get like a large internal volume in string units and weak coupling. So that like in this large n limit, we have like parametric control. And moreover, the moduli are stabilized in such a way so that this ratio of the Kaluza-Klein scale to the AdS scale goes to 0 in the large n limit. So these are scale-separated AdS4 vacua. And because we have like this simple scalar potential at hand, we can apply the flux backtracking procedure. So the split into fluxes is as follows. So the 4-form flux, which is unbounded, we want to turn into D-branes. These will be like D4-branes. And all the other ingredients, we want to turn into some background geometry. And as before, we can just solve for these flow equations, and we find this running of the scalars. You can also like write down the 10-dimensional dilaton. So the flow we find is one where like the internal manifold shrinks to 0 sides. It's like the same as with AdS5 at the singularity. And then here also like the dilaton blows up. And so we can write down the geometry in this way, again, in terms of this reparametrized radial coordinates. There's the coordinates which are along the branes, and then the extra dimensions. So the claim is that this is the singularity. Once we probe it by the 4-branes, then we can never find the DGKT CFT dual if it exists on these D-branes. So that's the claim. But okay, what are we learning at this point from this singularity? A first thing is that it's a seemingly fine singularity, so it does not obviously break any like consistency criteria. So this is already nice. We're like on the right track. I mean, but there's 2 things that are like different from the Fern-Rubin vacua. Firstly, like the dilaton blows up, so we have strong coupling at the singularity. So this is different, but it's actually good, because if the CFT duals to the DGKT vacua exist, they should have like a central charge or like a degrees of freedom scaling with n as like n to the 9 house. which is very large, and it should not be possible to obtain this with a perturbative counting of degrees of freedom. But this is not possible anyway because we get a strong coupling at singularity. Another scaling which might be interesting is like here the scaling for the non-compact coordinates. It also blows up at the singularity. It could have some interesting consequences, and definitely makes like the decoupling, the potential decoupling of the D4-branes from the bulk more subtle. Okay. So this is for the DGKT vacua. We can also apply it to other scale-separated AdS vacua. For example, very recently there's been like these scale-separated AdS tree constructions. We are like similar in spirit to the DGKT vacua. We can like apply flux backtracking in a similar way there. Like there's multiple groups working on it at the moment. Or there's these scale-separated AdS4 vacua, which are related to the DGKT ones by some T-dualities in massless step 2a. So there's no Raman's mass, and there we can, in a very similar way, like apply the flux backtracking procedure. So this flux backtracking procedure, I'm now applying it to scale-separated AdS vacua. It should be more generally valid. But I just want to I say like mention two cautionary remarks. Like first is like you need to know the full scalar potential to be able to do this. So you need to know the full potential and all the fields contributing to it, which might be relevant in the flow. And it should also like stay okay once you turn off the flux. For scale-separated vacua, this is like automatically satisfied, but if you have some consistent conjugation, this can become complicated. For example, we also want to do like try and find back like the brane picture for like these AdS7 vacua, but it's like very complicated because then you're not sure like how many fields you should include, and like the internal manifolds, they have like some anisotropy, so there's definitely more moduli you need to, or more fields you need to include. And secondly, the procedure works best and is most clear when you have like this clear split between a large N flux and the residual ingredients. And for example, like for scale-separated vacua like KKLT, we don't have this. So for KKLT, you'll have like fluxes and non-perturbative ingredients. A priori, there's no obstruction to applying the procedure, so we can try and apply it. We can, for example, just like try and turn off all the fluxes, but like these fluxes are now all bounded in a tupple, so it's a bit different than look at the flow purely generated by the non-perturbative effects. So this is something that can be done, and then you get like one flow which is very similar to the DGKT one, like where like the internal volume shrinks and the dilaton blows up. But then there's also another flow where like there's like a decompactification at a finite distance, and at this stage it's like not decisive which one you should take. So I would say like to for this more intricate vacua, like the flux backtracking procedure is not saying anything decisive yet. Okay, and now I want to end by talking a bit about the full DGKT brane dual and its decoupling. So I said before, like the claim is that we need to probe the singularity with D4-branes for DGKT, and then perhaps we can find back the CFT, which is dual to the DGKT vacua on these branes. And one way of making like doing a step towards checking this is by introducing the D4-branes in this background geometry in a very simple way. So I'll just like assign like some kind of harmonic functions for the D4-branes, and I'll apply like the harmonic superposition rule, and place these in like in a factorized way, just like on the background. And then once we have like this geometry, in terms of this harmonic function, we can try to solve like 10-dimensional Einstein equations to find the actual profile for the harmonic function this way. So then this is like the candidate like full geometry of like the D4-branes probing the singularity. And then we can check that this actually makes sense. So we probe the near horizon limit of this metric. And in the near horizon, then we actually indeed find that we get like some AdS geometry where all the moduli approach constant values. And like the vacua in this near horizon have like all the same properties as the DGKT vacua. So this is like a very non-trivial test of the flux backtracking procedure. And so it seems like we're on the right track there. Now that we have this 10-dimensional geometry, the full geometry, we can use this hopefully to learn some things about the conformal field theory. And one thing I want to discuss very briefly now is we could, for example, check whether these D4-branes actually decouple from the bulk, which is like a necessary requirement for holography to work. Okay, and so like one simple way of doing this, also how it was also like historically done, for example, for the D3-branes, is to look at the motion of like waves, like scalar waves or gravitational waves in this background. And we can write down like a kind of effective potential for these waves in this background. And then we find that there's like a potential, a barrier for these waves. And this barrier grows like infinitely high in the low energy limit of these branes. So this seems to like imply that indeed the D4-branes and the DGKT dual are shielded from the bulk by this infinite potential barrier, and that therefore decoupling is working. Okay, I think like next week some more perspectives on this will be discussed, and I'm gonna conclude here. So I introduced the flux backtracking procedure as a method to find the brane dual starting from the AdS effective potential. This way we were able to find a candidate brane dual for the DGKT vacua, which seems to be decoupling from the bulk because there's like this infinite potential barrier for waves. Okay, thank you for listening.
Thank you. Thank you for the very nice talk, Fien. Are there any questions?
I have a question.
Yes.
Can I go ahead?
Yeah.
Yeah. Okay, so thanks for the talk thing. So I was wondering, like, regarding this, what you were saying about which part of the potential you dualize or not, like, because in some of the examples you presented, it is indeed kind of like natural to dualize one part of it because you can change the flux and so on. But for example, like, could you dualize in the same example, dualize different parts of the potential and get the same results or not? I mean, for example, in DGKT, you dualize the part that goes with the end flux that doesn't enter the tadpole. But what happens if you dualize also some other part or some flux that enters the tadpole, but you do it consistently? Do you get the same kind of results, or why is that not legal, or like, is this clear?
Yeah, so in principle, a priori you can do it, but I think then things will be more subtle because the fluxes that enter into tadpole, they talk, there's like terms in the potential energy like that talk to each other. So then it's not like clearly separated from the geometry, and I think eventually it's that it will not make much sense, or you will need to do some more work to make it work.
So let's say there's the sufficient conditions that you can decouple it, kind of, but let's say you don't have like a full, because you were saying characterization, like necessary and sufficient conditions for this to be.
No,
Okay.
not investigate. And I know it works if it's like clearly clear,
Yeah, yeah.
if the fluxes clearly separate, but then that's as I was discussing for KKLT, like there's no real obstruction, but maybe I don't know yet actually.
Okay, thank you. I have another quick question, but if you need to go, can I go ahead? Well, I will go. If not, just cut me.
Yeah, please. We finished early, so
okay.
plenty
So
of time.
in the cases when you like subtract this part and then you are left with the residual scalar potential, is it always like in the picture that you were showing that this potential kind of goes towards minus infinity when you approach this flow that you're following, or is it ever the case that it
sorry,
goes?
which okay, minus wait, you mean minus infinity at the singularity?
Yeah, exactly. I mean, if I
So
remember
far for the
correctly, your drawings
examples
were
we
like this,
tried,
right?
so far
Yeah.
for the examples we tried, yes.
Okay.
But not for like the DGKT. No, I mean the KKLT one that was different, but the slug, yeah, maybe it
Yeah.
doesn't work there.
Okay. Okay. I see. Thank you.
Anybody else? If not, I have a quick one. So Fien, on most of the equations you just wrote the potential with the schematic dependence on the overall volume and the dilaton. But what if you look at explicit realization of the GKT with more moduli, with a more complicated setup? Does anything change? I guess.
No, because
No.
then I think like for DGKT, then all the yeah, if you include more moduli, that will not change anything because they will just like in an isotropic way.
Scale the flux the same way. So
Yeah,
it's all
scale. So it does not it doesn't add anything.
anything. Not even if you have complex structure moduli or no, I guess.
Complex structure moduli. I think they will just be frozen. Yeah, no, I'm not sure, but I think it will not add anything.
Okay. Thanks. Anybody else? Okay, if not, then we can stop the recording and you can start uploading the screen sharing, Ben.
Yeah.